In this lesson, we're going to have a two-part lesson. The first one is going to be talking about simplifying radical expressions that are a little bit more difficult. And this first group of problems are going to work out nicely. We're going to have perfect squares, perfect cubes. But then the second video, part two, we're going to have things that are not perfect squares and perfect cubes. And we'll figure out how we deal with that. So let's do a couple of these that actually work out pretty nice. We have perfect squares, perfect cubes. And let's see what we got. So we're going to be talking about these properties where if you have the same square roots or same cube roots and their individual pieces, you can combine them, or if you have multiple pieces inside, you can break them apart into individual terms. That works with fractions as well. If you break a fraction up, you can individualize this into the nth root of whatever the numerator is, divided by the nth root of whatever the denominator is. Or you can take it, as long as the roots match, you can also combine them into one fraction. And different circumstances are going to want different things. So let's take a look at what we got. So we're going to simplify a couple. So the first one, if you have the square root of 2 times the square root of 50. Sometimes it's good to just take these two values, they're both square roots, and combine them together. So since they're both square roots, they're still multiplied together, but we can multiply the 2 and the 50 together, which becomes the square root of 100, which now is a perfect square. So square root of 100 is 10. All right, and there's a lot of different ways to do this, but sometimes it's just nice to just throw them together, see what happens. All right, so other times you have a number like this, and this is where we're going to do a little bit more of in this part 2, but this one is one of those where it's not a perfect square, so we can actually take and break this apart. And there's multiple ways to do this, and let me show you one approach, and then we'll kind of talk about a second one. Is we're looking for perfect squares that go into 20. And something that's smaller than 20 that's a perfect square is 4. So you could break this into 4 times 5. So we can individualize this into 4 times 5. And the reason we chose 4 is because now when we break apart the square roots, this is a perfect square, and so you can square root the 4 and get 2. 5 can't break up any further, and that'll be your answer. Now a second approach to this is taking this 20 and doing a factor tree with it. And we'll do this a little more often on the part 2 video. But this breaks into, let's say, 2 and 10, and this breaks into 2 and 5. And these are our primes, can't break them apart any further. So if you list this out, you have a 2 times 2 times 5. And the whole idea is square rooting something is you're looking for perfect squares. So you're looking for pairs of the exact same number. That is our pair. So that is what we can square root. That's what's going to come out of the square root. And this doesn't pair up with anything, so that's actually going to stay on the inside. So it gets us the exact same result. And we'll do a couple more of those in the second one. It's part 2. So third one. Let's say if you have the cube root of negative 2 times the cube root of negative 4. Individually, they're not perfect cubes. However, if you can combine it together, so you have the cube root of negative 2 times negative 4. That's going to make the cube root of 8. And 2 times 2 times 2, it becomes 8. So there's 3 2's that would make up 8. So 8's a perfect cube. And we get a 2 out of that. So if we have fractions, 1/2, square root of 1/2 times the square root of 1/8. Again, kind of like this first one, sometimes it's just nice to put the values together, just see what happens. So if we're going to multiply these two fractions together, we're going to have 1/2 times 1/8. So the numerator times the numerator will get us a 1. Denominator times the denominator will get us a 16. And now we can look at this fraction individually and do the square root of 1 divided by the square root of 16, which gets us 1/4. Square root of 1 is 1, square root of 16 is 4. So that's one where sometimes, again, it's nice to just put things together, you might create perfect squares or perfect cubes or whatever that root is that you're dealing with. Let's do another. So if you have the square root of 3x over 2 times the square root of x over 8, you can combine them together to one big fraction. So 3x, numerator times numerator, is 3x times x is 3x squared. 2 times 8 gets us a 16 again. So we're looking at the numerator is 3x squared, the denominator is 16, and we're going to kind of break this apart very similar to what we did up here, where like this we're trying to pull out a perfect square, and x squared is a perfect square, so we can look at that individually from the 3. Square root of 16 is 4, and the square root of x squared, squares and square roots undo each other, so that would just leave you with an x, and the square root of 3 we just have to leave as the square root of 3 with our denominator of 4. Alright, do a couple more. So if you have the square root of 45 over the square root of 5, neither of them are perfect squares, but just like we can break apart a fraction, we can combine the fraction. As long as the roots match, we can just make it as one big problem. So that'll be 45/5, which we can reduce that fraction down, and that fraction, 45 divided by 5, is actually just 9, and we can square root that very nicely. So like I said, sometimes there's times where you just want to multiply the pieces together, and they may create a very nice value. Sometimes we're going to want to break them apart so we can pull out perfect squares. Let's do another one. So if you have the cube root of 54 x cubed y to the 7th over the cube root of 2y. So we got a whole lot of things going on. It's probably best to just throw it all together onto one big umbrella of the cube root. So they're all cube roots, so we can write it as 54x to the 3rd y to the 7th over 2y. And we can reduce what we can. So the 2 will go into the 54, make that a 27. And then one of these y's is going to cancel one of those y's. So you don't have a denominator anymore. So you're talking about now the cube root of 27 x to the 3rd y to the 6th. And again, it's all about, we're looking for 3 of the same kind. So 3, if you multiply a bunch of 3's together, it turns out to be 3 times 3 times 3. So that's one big group of 3's. So we can cube root that. X to the 3rd is exactly the same idea, except they're all x's. So there's one group of x's that we can take out. And y to the 6th is 2 of those groups. So you can take out 2 groups. So if you cube root y to the 6th, you're looking at how many groups of 3 you can take out. You can take out 2. And last problem. If we do the square root of 16 x to the 4th y to the 6th. See where that goes. So same idea. Can you square root the 16? Yes. That's 4, because we have a 4 times 4. So you're looking for a pair, the exact same thing. Here you're looking for pairs, because we're doing a square root. And this we have exactly 2 pairs with nothing left over. And here we have 3 pairs. So it'd be y to the 3rd. All right, and that's part 1 of simplifying radical expressions that are a little bit more difficult.